Hi, everyone. Today I'm going to talk about not complex event-driven applications with Kafka Streams. Why not complex? Because complexity is not a desired state of a system. Complex applications tend to be hard to maintain, scale, and not very reliable. In my presentation, I will talk about a specific problem we had at my company and how we solved it. I will demonstrate few techniques we used to simplify the initial complex design and the benefits that came out of it. But that's not all. I will also talk about other key components like schema, registry, and lead scoring app. I hope you are interested, so let's start. Hi, I'm Michał. I'm a staff data engineer at Simple Business. I like simplifying things, and as you can see on the attached photo, bright t-shirts, although today I'm wearing the black one. You can find me on Twitter and on GitHub. So agenda for today is I will walk you through the problem. I will talk about key prerequisites that are needed for the robust system, mainly about events categorization and schema registry. Then we will go to the solution, where I will talk about Kafka Streams and what we learned about Kafka Streams, about the architecture and the design of the application, and then about the lead scoring. And I will summarize everything at the end. So the problem. Simply Business is an insurance broker. People come to our site to find covers for their businesses, like public liability cover, employer's liability, personal accident, or tools cover. They will find us on Google, and then we'll go to our site. They will select the trade, go to the questionnaire, where they will need to fill in a few questions that are important to get the right quotes. So once they answer all the questions, they will see a quotes comparison page where there are prices of the insurance from different insurers. Then they will go to the checkout page, pay, and at the end, they will get a proof of policy, a certificate. This is a happy path. Usually what happens after seeing a quotes comparison page, people will leave. They either go to shop around or they will not be certain that they answered the right questions correctly. So in that case, we would like to call the customer. The requirements from the business are as follows. Given a customer who needs a policy, and they can be contacted, and they didn't purchase a policy yet, and there's propensity to purchase is high, then call the customer. When we saw those requirements, we had many questions, like when to call. People can still be on the journey, so we cannot call them immediately. We should wait. Should we call everyone? No, because we only have a limited number of consultants, so it wouldn't be a cost-effective and even not possible to call every customer. How to ensure we don't call the same person twice or more? We need some state. How to measure a propensity? What's propensity? It's likelihood to purchase, but how to get it? And how to collect all needed data. There are plenty of microservices that hold data for a given part of the journey. And there were more questions, but they are the most important. We thought about this, we analyzed, and we came up with those application requirements. Application will have to create and reach the duplicate and manage the contact request. That was the name of the entity that we called a contact request. It will have to also delay sending to a dialer. Dialer is a system that is responsible to making the calls, and we will need to prioritize those calls in some way. Before I move to the solution, I would like to talk about key prerequisites, key components of any robust architecture. I will assume that since you're in this talk, you already have a Kafka cluster and many microservices that exchange data over topics. The next thing that I would like to talk is events categorization. Events word is pretty overloaded term, and it means different things. And there are different categories of events that might be treated differently. At Simple Business, we came up with a few categories, mainly domain events, domain entities, front-end events, and application internal events, and few technical events types. So front-end events are any types of events that come from browsers, where it's like clicks, page views, scrolls that are helpful for analysis and the flow on the site. They're application internal events that are used internally by an app and not shared with any other application. But I would like to focus on the first two. So domain events are notifications that something important happened in a given domain. Those events are important for business. There might be some metrics based on those events, and those events are also important for external services. They usually have a minimum required data, but they also should have a reference to some entity, and they will go on one topic. So an examples of those events are customer created, policy purchased, that will be published from some bundled context, and they might go on one topic, partitions topic. So here in my diagrams, it's our simplifications. All those topics are partitions. Domain entities, on the other hand, represent some kind of entity that application can keep in some state. So it could be an entity that is returned through REST API, like customer/1 returns an entity of the customer. And the way we replicate it to Kafka is through CDC patterns, like CDC techniques, Debezium, change data capture. And there's a one topic per entity. An example here, there's a customer entity and policy entity that goes on Kafka. The second important prerequisite is schema registry. So schema registry is a centralized repository of schemas for events and entities that are shared across the whole company. Schemas ensure correctness. Every schema will have some kind of validation on it. And it will help with data evolution as schemas are also versioned, and they guarantee backward and also forward compatibility in some cases. And in a sense, schema defines a contract between services and data teams when they analyze data. There are many off-the-shelf schema registries. The canonical one for Kafka is probably Confluent Schema Registry, but there is also even Bridge schema Registry from AWS, Cloudera Schema Registry, and Igloo Schema Registry from Snowplow. I would like to talk briefly about the last one because that's what we use. The main reason why we use Igloo is because we use Snowplow, and Snowplow is an open source project to track events from different sites and different places. And we used it way before we even introduced Kafka. So you can read more about Igloo on GitHub, but in essence, it hosts and works with JSON schemas mainly, but you can add also Abra and other types. It follows semantic versioning of schemas, similar to versioning of libraries. And you can keep your schemas on GitHub, which we do, and we really enjoy this paradigm. And when a pull request is merged, the schemas will be published to some repositories on S3 or any kind of HTTP repository. And in an essence, you have an application. In your application will have Igloo client that has resolver and cache. Through resolver, you will say where the schemas lives. Then you will, having your customer entity, you will convert it to Igloo JSON. That looks, the structure is schema and data. And schema property defines what exactly the name of the schema, name of the event, and where it is. The structure on the disk, on the repository, is that you have a vendor, event name, then format. As I mentioned, you can have different formats. The JSON schemas are preferred. And then you have different versions of those schemas. And as in the code, it's kind of major, minor patch. In schema world, it's model, revision, addition. When you add addition, it's then assumed that it's backward and forward compatible. And obviously, JSON schema looks like this. You have title, description, then you define the properties, what type it is. You can add some validation and information which fields are required. So there are a few benefits from having this kind of schema registry. It's not only for Kafka. GitHub pull requests helps a lot with defining the schemas and finding problems with the naming. So there's usually many comments on shared schemas. You can define maintenance files. So if you have if your team consumes some event, if you have application that consumes some events like policy purchase, your team can add itself to a maintainers file and it will be notified when something has changed. And obviously it has on write and read validations. Customers can define what major version they can work with and so on. So having those prerequisites is pretty important for any kind of robust system. Having a categorization of events is important because then system will know what they want to consume to create their state. And schema registry is just mandatory because you don't want to end up with a new event that something was changed and your system didn't expect that. So back to the problem. As I mentioned, at Simply Business, we sell insurance, and if someone didn't purchase it on the online journey, we would like to contact them. So the thing we would like to create is in the middle. And just for the context, there are many applications that write to Kafka, and they usually don't have any REST API. So our application that we would like to create will be reading from Kafka, aggregating some state, and then publishing something back to Kafka for the dialer system. And the app requirements, just for a reminder, we create, enrich, manage, delay, buffer, and we would like to prioritize. To solve that problem, we picked Kafka Streams, and there are a few reasons for that. First of all, is simplicity. Kafka Streams is just a library that you can embed in your application. You don't need any external cluster. We before been having many applications in Spark Streaming, but after a while we decided that Spark Streaming is not the best solution for us. So we went with Kafka Streams. Another important thing about Kafka Streams that it was supporting joins. So we could easily join some streams of data and enrich them with and create the state. And as I said, it also provided state stores, which allowed us to store some kind of state internally in the application without a need for an external database. Those state stores on Kafka Streams itself is fault tolerant because it has changelog topics. So if application dies, before it will went up again and serve and consume events, it will guarantee that state stores its up, back, and live. And Kafka Streams and Kafka per se from version 0.11, I think, or 0.10 had transactions. So it was guaranteeing effectively one processing, which was a big deal for us. So the design. And I just don't want to say that Kafka Stream is perfect. It has some flaws, but I guess it will be a different talk for that. So what we did in version 1, we decided to listen to domain events and reach through joins, manage state in a state store, buffer, so we didn't want to send immediately to the dialer messages. And once some state is ready to be published, we were publishing back to Kafka. So in our streaming application, we started with a state store that was keeping contact requests. And that contact request is an object that had some kind of user ID, contact details, and many more properties that were needed for some kind of filtering. So we started with creating a contact request. So there was some kind of domain event that was creating a state, but first it had to be enriched with some other stream of data. What the state is created, we had to buffer it. We didn't want to send directly straight after the state is created. We had to set some timeout. So there was another state store and processor node that was keeping track of it. There was other entry paths to create a contact request, and it followed the same logic. There were events that were deleting contact requests. There were many that was deleting those. And there were events that were updating those contact requests. And when we built it, it worked, really worked, but mainly locally, all the tests were passing. What we noticed when we deployed it to the staging environment, that we built a massive topology of computations. And to be honest, we were expecting that the topology might be massive because there were many things happening. But we didn't expect that there's going to be only one subtopology, which was joined by one single state store. Let me give you a small recap about work allocation in Kafka Streams, so you understand a little bit better what I mean by just one subtopology. So in Kafka Streams, when you build your application, you build a topology of some kind of computation. You have an input topic and output topic and some nodes that transforms the input data. And the topology can be broken up into subtopologies. The max parallelism is determined by stream task. And stream task is an independent unit of computation that can run on itself and hence can be parallelized. The number of stream tasks is mainly determined by the stream partitions, but not only. And stream partition is just a partition on the input topic. And stream tasks don't share a state store. So if we had a state store that joined many computations, many subtopologies, we will end up with only one subtopology. Let me show it quickly. So in a simple topology, we have input topic with 3 partitions, some processor nodes, and output topic. And if we want to know how many tasks will be created that can run independently, it depends on the input partitions. So there's going to be 3 tasks that can run on threads, on separate stream threads. And the task naming, just so you know, it's subtopology number and partition number. If you deploy your another application instance, the work will be allocated equally. And then you have your desired state of your application and computations. If you have a bit more complex topology, but it doesn't really share anything, you will end up with 4 subtopologies. And that also means that you will have 4 tasks that can run in parallel. But if there's one thing that joins all of those topologies, you will end up with only one subtopology and only one task. So the outcome of the version 1 of our streaming applications everything was intertwined with that state store. And there was lots of repetition because different entry paths were doing very similar computations and creating similar state. That caused also limited parallelism, as I described before. And one thing I want to convey is that it was easy to build, but after all, it wasn't simple. It wasn't simple to scale. And there were a few techniques that we could use to create more stream tasks, like introduce some topics through in some entry path, but still we thought it won't be simple. So we thought about this and decided to improve it. So we came up with the version 2 of the application. And the main thing that we were inspired is this quote from Eric Evans. Model information about activity in the domain as a series of discrete events. Represent each event as a domain object. The main thing in this quote is the domain, and that's what we forgot when we built the system. Our new application had its own domain, but it was working with some outside domain. What I mean by that outside domain was anything happened on all domain events that were published outside. So there we had codes created, policy purchased, expired, consent removed, customer created. Those events came from outside, from different bounded contexts. But on the inside, what we had a contact request. And this, what we should have modeled a little bit better through specific commands to the contact request state. So contact requests can be created, removed, scheduled, prioritized, triggered, blocked. And a good technique, a design pattern, how to join the both, is an adapter. So adapter translates outside domain into inside events, commands that are understood by the application. And what I mean by that, let me show on the diagram. So we have the same thing as before. We have our Kafka Streams application in the middle. And the first thing that we introduced is some adapter that was joining events and entities from the outside and creating a new command. Let's look on the code. This will clarify things a little bit. So we had a stream of quotes created that we had to join with customers table. That was creating initial state. We were selecting the key for partitioning and then mapping that initial state to command create contact request and sending it to internal app commands. And the same pattern we followed for all other entry paths. So we had policy purchase stream. We were mapping that event to internal command to delete contact request and sending to internal app commands. And we ended up with a layer of adapters that were pushing commands in some internal Kafka topic. And those adapters were repeated, even though they were getting different events, they were sending similar commands like create, delete, or prioritize. And the core logic, the business logic that was applying was in single place, and that single place was handling state changes. And the logic looked kind of like event sourcing. We were getting to our function a state and incoming command, and it was returning a maybe state. If you check the code, so we had some transform function that was taking optional state, a state change command, and returning optional state. And in a case, we had some pattern matching where if there's no state, but there's a create contact request command, we were creating a state. If the state was already there and there's a create contact request, we were deduplicating. If trigger, then we were changing the status. In the code, a bit more visual, we had a transformer. In Kafka Streams, transformers are the place where you can interact with state stores. So some command was coming in to our transformer. It's a one-by-one processing. We were applying our business logic to that command. Then that command changed the state, and that state was pushed down the stream. And later, we had a stream of changed states, and based on some predicate branching logic, they might went to different streams of data that are downstream. Code again. So we had command stream transforming the values, passing the core logic function and store name. We got updated state stream. And then we could filter based on some status on that state, like if status trigger, we should map that state to a event, outside event, domain event, and send it to topics to dialer. So that topic dialer is a topic which was used for the dialer communication. And if it's prioritized status, then we were mapping it to a different domain event, contact request prioritized, and doing the same. So we ended up with another layer, in a sense, a gateways adapters, or you can call it whatever you want, but we were working on the changes of the state of contact request. And at the end, our application looked something like this. We had layer of adapters that writing commands. There was core logic that was applying some function to incoming command and existing state. We had a stream of state changes and sets of the other layer of, you can call it adapter or not, or some nodes that were processing that state change and doing many other different things. So there are many benefits of this architecture. So mainly, there's one input stream to manage the state. So it's kind of, you can think about functional core, and you had imperative shell with adapters. So then that functional core was simple to test. We had increased parallelism, and if you can break it up. So the thing that you can break it up is adapters. You move it outside, but they were already an independent stream tasks. And one thing that was, I didn't talk before, but we had a requirement for audit log. And business wanted some audit log for analysis and reports. And we also wanted that for debugging. So we have some way to see what happened to the state. And with Kafka Streams, it's pretty easy because first you have a changelog topic, and we had a commands topic that we could, and we did, with Kafka Connect replicate to some warehouse or any other place that it's easy to query. So in summary, for version 2, we design our system more in terms of domain-driven design. We introduced internal commands that were shaping the state. We had adapters that were translating incoming events in those commands that our functional core understands. And then we had gateway adapters that were translating an internal state into domain events. Thanks to the second design, we managed to fulfill 3 out of 4 requirements for our application. The last thing that left is prioritization. And what I mean, and prioritization, it's quite complex topic, because how do you prioritize? There are many, many factors that you can take into your algorithm. There's number of interactions, type of covers, what trade a customer selected, what was the premium of quotes, how much time a customer spent on the site, number of quotes were generated, many, many more. You can even take browsers, email addresses. So how can you do this? We didn't know initially, but we knew that we want to A/B test. So we know once we hit the jackpot. So some algorithm or some way to properly prioritize those contact requests. What we started with was some heuristics-based rules. So we had rules saying this or that and that, and in this case, the priority is 10 or whatever. That worked, we were A/B testing that. But then we talked with our data science team about lead scoring, about predictive lead scoring. And lead scoring is a technique used very often in sales and marketing, where you score interactions by your customer and give it some number. And we also had another approach where we had heuristics and lead scoring, because lead scoring only gives some number. We had to apply it, maybe add some time. So the most fresh leads are better than the previous ones. Or we not always were getting the lead scoring events. So in that case, we had to have some way to still prioritize. But all of those techniques we were A/B testing. Let me talk a bit more about lead scoring, because that's where it was the most fun to work with. So we had data scientists that worked with Python and SageMaker, creating machine learning models with XGBoost. And they've been working hard. It's not a simple problem. But once they managed to create the models that they thought are good, we had to somehow apply them. And we couldn't have a batch lead scoring, which could be good for marketing. We needed a streaming application, new real-time lead scoring, so we can consume in real time and score our contact requests. So we created a new applications that was getting loads of data from Kafka about the attributes that were needed for the model. And once it managed to get the score, it was publishing a lead scored event. So a quick diagram. So as I mentioned, we had a new lead scoring application. It had a store of user sessions, and in that store, it were keeping a data, the properties that were needed for the model. Once it got enough number of attributes, it was making a call to SageMaker where the model was kept, and in the back, it was getting some value, and that value was a score. Once it got the score, it was pushing on some Kafka topic. And it was doing constantly until it notices that customer left. There was some timeouts to send events again, even if something has changed. So on the right-hand side, we have our dialer system. And before every consultant, there was a call queue with a priority. So that's how we managed to prioritize. So we introduced that new lead scoring application into the flow. It was sending an event. That event was through adapters translated in some internal command. And our application's context management was keep updating the priority value in the call queue. Sounds simple, right? It wasn't. But the summary is that we ended up with many experiments and we designed our solution for A/B testing. But the most important bit is that through predictive lead scoring, we increased the return on the call spend by over 50%, which was massive. So let me recap everything. In the prerequisites, I talk about events categorization, which helps a lot for the other application to know what they work with. Schema registry is just a must. If you want to have a robust system, events has to be schemed, versioned, so you don't break something accidentally. You should strive for simplicity with your designs, and Kafka Streams is easy to use, but there's some hidden complexity that you need to know about. And in those cases, domain-driven design helps. It at least helped with our case to simplify the solution. And machine learning is just a cherry on the top. Thanks to predictive lead scoring, everyone was happy. Our consultants contacted only the customers that have a high propensity to purchase, which led to fewer calls that ended up with just hangups. And our customers also got the help that they needed. Thank you. That's it for today. Any questions?